Hello, my name is Samizadeh Nikoo. It's a great pleasure to deliver this talk at IEDM. The title of my talk is High Performance Gallium Nitride Electronic Metadevices Towards 6G Telecommunications. This is the output of my postdoctoral research at ETH Zurich, where I was working together with Professor Wang. So let's take a look at the progress of telecommunications over the past decades. We can see an exponential increase in the available data rates, which was necessary to deal with the demands of our society. And in fact, the future of humanity relies on more and more connectivity, and that's why we need networks with higher capacities, and that's why we have to move towards 6G and beyond. So in order to increase the capacity of telecommunication networks, in fact, we need electronics that can operate at higher frequencies. In fact, 4G was operating at microwaves, 5G is now operating up to millimeter waves, and 6G is expected to operate at terahertz frequencies, which is the challenge for electronics. The reason is that the traditional way to speed up electronic devices has been by shrinking the size of the transistor. So here we see the cutoff frequency of transistors versus the gate length, and we can see how shrinking the size increases the operation frequency, but this trend saturates at a gate length of about 25 nanometer, while the cutoff frequency is still below 1 terahertz. So we can say that the progress of telecommunications has been evolutionary so far, but to get 6G and beyond, we need something revolutionary. So we can take a look at the limitation of electronics, which causes constraints at terahertz frequency. So we can take a look at the specifications of one of the best gallium nitride transistors that has been ever reported in the literature, and we can see that the source and drain resistances are larger than the channel resistance. And this is a big challenge in nanoelectronics, because as we shrink the size of the devices, at some point the electron injection and extraction totally dominate the active region of the device. And this is not just for gallium nitride, but it's a general limit for silicon 3,5 and even 2D materials. This is a severe limit for nanoelectronics. So these ohmic contacts limit the performance of nano devices. In fact, the transconductance and the operation frequency of amplifiers, it limits that, and also it limits the cutoff frequency of switches and modulators. And this is where the concept of electronic metadevices come to the game. So optical metamaterials have revolutionized optics. The core idea is that sub-wavelength manipulation of electromagnetic fields results in extraordinary optical properties and exotic properties and functionalities, such as negative permittivity and cloaking, in fact. So just this year, we proposed the concept of electronic metadevices, where microscopic manipulation of radio frequency fields results in extraordinary electronic properties. This is an analogy to metamaterials, optical metamaterials. Here we see the field pattern in a two-terminal switch. This is the electric field capsulated between a top metal and a 2D electron gas underneath. And although the operation frequency is just 100 gigahertz, which corresponds to the wavelengths of roughly millimeter range, we see oscillations in the micrometer range. And we will see how this field manipulation leads to, in fact, modifies the microscopic properties of the device. And in fact, John Pendry used the optical metamaterials and proposed a way to realize a perfect lens. Using electronic metadevices, we proposed and realized a way to form a perfect contact between a metal and a semiconductor. And this is what we achieved, and it was reported in this Nature paper, that in fact the contact resistance and the total arm resistance are far smaller than semi-metal and metal, which are the traditional contacts. So in this talk, I will describe more in details the concept of electronic metadevices, I will present the supremacy of electronic metadevices in terms of the cutoff frequency. Then I'll describe experiments showing high performance linear and nonlinear operation of electronic metadevices. I will present integrated electronic metadevices for terahertz switching for operation above 300 gigahertz. And finally, I'll showcase performance, an application of electronic metadevices as high-speed millimeter wave modulators. So, about the concept of the meta device, in fact, we have two steps. We need to discuss about two things. The first thing is a sub-wavelength mode that exists at the interface of a metal and the 2D electron gas. So we have a top metal, we have barrier, and we have 2D electron gas, and this barrier is quite thin. And solving Maxwell's equations under electrostatic assumptions at the barrier would lead to this equation. This looks like the wave equation. It has a second derivative of electric field, which is equal to constant times electric field, but it has two differences. One is this imaginary term, and the second thing is that this coefficient is much larger than what we have in conventional free space wave equations. So this equation has two eigenfunctions as we represent here and as we plot here. And in fact, the effective wave number of these eigenfunctions can be represented by this equation, and this is much larger than omega square root of mu epsilon, which is the free space wave number. And that's why this is a sub-wavelength solution. And we can see this in a simulation. In fact, this is this graph. This schematic shows the same structure. We just have a discontinuity on the gap on the metal layer, and we can simulate the electric field encapsulated between the metal and the 2D electron gas, and we see these kind of damping oscillations that happen in micrometer range, which is far smaller than the effective wavelengths. And here we just considered some typical numbers for sheet resistance and the barrier thickness and also the relative permittivity. So the second thing that we should consider and we should talk about is the sub-wavelength metallic features of these devices. So in the left side, we see a schematic of the same device that I described, and this is the electric field that we just talked about. And if you replace this straight gap of this device with the array of a stripe to have a zigzag gap like this, then these sub-wavelength response will collectively interact with this metallic stripe array, and it leads to manipulation of electric fields at the barrier. And this field manipulation leads to extraordinary electronic properties, as we can see. So basically, the magic here is that if you look at two adjacent stripes, these two stripes, they are connected to two different terminals, but the polarity of electric fields are identical. So we can see that these are two different terminals. One is injecting current to the other one, so this is the direction of current, but the electric fields are on the same direction. So if we calculate the line integration of electric fields from terminal 1 to terminal 2, then whatever happens under the terminal cancel out each other, almost cancel out each other, and what we have is just what happens at the gap. So this is a very good contact between the terminal and the 2D electron gas underneath. And we can see these by looking at the current density of the 2D electron gas. So this is what we have in a reference device. As you can see, the current spreads out of the gap, which means that we have a lot of losses, we have a high contact resistance, and so on. For the meta device, the current is very confined at the gap, and this is a very good benefit for this device. So in this Nature paper, we already showed the supremacy of electronic meta devices in terms of the cutoff frequency. So this is the experimental setup. I did the measurements at Fraunhofer Institute in Freiburg. And we have the device under test and 2 terahertz probe. These 2 probes can go up to 1.1 terahertz. And by measuring the impedances in the off and on states, we can in fact estimate the cutoff frequency to be 18 terahertz. which is far higher than what can be achieved with traditional electronics. So these are the R on and C off of electronic meta-devices with 3 different geometries, terahertz, millimeter wave, and microwave, as we can see the geometries here. And here we just scale the number of stripes, and we see how the R on and C off scale. So we have 2 important things from these results. The first thing is that even for terahertz devices, the dimensions are not very, very small. So still the critical dimension is above 100 nanometer. And the second thing is that by scaling up the devices, in fact, their performance gets better. And the reason is that as we increase the number of stripes, the collective interaction between the sub-wavelength mode and the metallic stripe gets more pronounced. We have more pronounced field manipulation, and we get a better performance. And that's what, in fact, happens. So here we want to take a look at the important features of these devices, meta-devices, for future telecommunication circuits. So we need devices that are highly linear when they operate in on and off states, and we want to have a very good nonlinearity when they are switching, for switching application, for mixing, and frequency multiplication. So here we have the measured impedance versus DC bias voltage, and we can see that first of all we have a full symmetry because the device has a symmetry geometry, and the second thing is that we have 3 operation modes in this graph. So at 0 volt, when we have a low impedance, the device is in the on state. At high voltage, when we pass the threshold voltage, we have the off state, which is the high impedance, it's a blocking mode. And when we bias the device close to the threshold voltage, in fact, we have the nonlinear regime, which is for mixing and frequency multiplication. And we have 2 linear regimes and 1 nonlinear regime. So first we focus on the linear regimes. Electronic meta-device has 2 important features that guarantees a very good linear operation. The first thing is that the impedance is flat at 0 bias because of the symmetry. And this flat impedance leads to a very good linear performance in the on state when we are at 0 volts. And the second thing is that thanks to the very high breakdown voltage of these devices, this device can be biased at higher voltages, which avoids a forced turn on when we submit the device to a high amplitude signal. So these are good things for the linear operation of the devices. So we characterize experimentally the linear operation of these devices. This is IIP3 experiments. So we have 2 tones at 14.9 gigahertz and 15.1 gigahertz. And this is the device geometry. So we have the results for, in fact, different number of stripes. And as you can see, we have very high linearity. In fact, for the device with 16 stripes, we have IIP3 of 44 dBm, which is equivalent to 150 watt per millimeter. And in addition to that, we have experiments on high power operation of these devices. We used a 27 gigahertz power amplifier that can go up to 1 watt or more than 1 watt. So we submitted the devices with different number of stripes to this source, and what we have, in fact, is a very high 1 dB compression points that are shown by the white points here. For the device with 16 stripes, we could never reach the 1 dB compression. In fact, at 29 dBm, around 1 watt, we have only 0.3 dB compression, and this is equivalent to a 1 dB compression point above 6 watt per millimeter, which is very high. And also for off state, we have a fully linear operation showing that there is no forced turn on. Here we bias the device at 20 volts, and this is very good because no terahertz switch can withstand 20 volts. For this device, we can really go to off state and we can block very high power, which is a very important feature. So then we focused on the nonlinear operation of electronic meta-devices. For this, we evaluated the second harmonic generation using these devices. And for the output bias, we just fixed it at 0 volts. And for the input bias, we had a sweep from -7 volt to 0 volts. And also, we swept the input frequency. at the output, we had an spectrum analyzer that collected the signal, and we evaluated the second harmonic generation. So here what happens is that in each graph, each point corresponds to the conversion gain. Of course, it's a passive device, so we have negative gains. And as we can see, by increasing the number of stripes, in fact, the collective interaction gets improved. We can also see that the second harmonic generation is much better. In fact, we obtain values better than -15 dBm, and here we see the highest conversion gain versus number of stripes, and we can see that electronic meta-devices approach the theoretical limit of ideal diode, which is very good. So this device is excellent in linear operation and is also close to ideal limit of a diode in the nonlinear operation. So in the next step, we showed integration of electronic meta-devices, what I call from meta-devices to meta-switches. So this is an integrated switch that includes 3 meta-devices in series and shunt configuration. So the output voltage is always fixed above the threshold, let's say 5 volts. When we apply 5 volts at the input, then there is 0 volt across the series meta-device, so this is in the on state, and the 2 shunt meta-devices are in the off state. And then what happens is that the entire switch is in the on state, in fact. And when we apply 0 volt to the input, then the reverse happens. So the 2 shunt devices become on, and the series meta device becomes off, and the entire switch is in the off state. So we characterize the, in fact, transmission and reflection from these devices. We don't end the embedding. We measure 2.7 dB insertion loss in the on state and 15 dB isolation. And in terms of reflection, so the device has a very good rejection in the off state, and also in the on state, it has a very good matching. So in addition to the very good insertion loss and isolation, and also matching of this switch also provides a very fast dynamic. So here we see voltage versus time, and we can see that, in fact, at the carrier frequency of 90 gigahertz, we can have a very fast switching. This is 3 gigahertz switching, and this is the experimental setup that we use to evaluate these switching speed measurements. So we have the LO signal, which is this carrier, it's 90 gigahertz, and also the control signal, which set the state of the switch. We have a combiner, and we apply that to the device under test, and we measure the output using a high frequency oscilloscope. And by zooming in to the switching waveform, we can see a better we can see, in fact, switching time better than 20 picosecond. And this is very promising because this is a very good switch with a static performance and also very fast dynamics. So this is very promising for mixing applications and modulation for future telecommunication circuits. So we showcased the application of electronic meta-devices in millimeter wave data transmitters. This is the schematic of the experimental setup that we used. There is an arbitrary waveform generator that streams data, and this is, in fact, a QPSK modulated wave at low frequency. So this is centered at 10 gigahertz. And then a signal source generates a continuous wave at 40 gigahertz, and the combination of these two is applied to the meta device, which is biased close to the threshold voltage. And so the meta device linearly upconverts the QPSK modulated signal into millimeter waves. And this is the upconverted signal corresponding to QPSK modulated at from 1 gigabit per second to 10 gigabit per second. And this is what we have, constellation diagrams of these modulated waves showing that we can demodulate, and so the upconversion was totally linear. So then we focused on measurements at higher frequencies to perform QPSK transmitters, to have QPSK transmitters at 100 gigahertz. For that, we use the 110 gigahertz UXR oscilloscope of Keysight. And here is what we have. So this is the device under test. And we have a local oscillator. We have a frequency up converter of VDI. And the AWG here generates the data that is modulated with QPSK at 10 gigahertz. So this is the zoomed in part of the device under test and the probes. So here we have the 90 gigahertz CW signal coming, the AWG. We have a combiner, and then there's a bias T that bias the device close to the threshold voltage, and at the output we have a QPSK signal at 100 gigahertz. So we see again a schematic of the experimental setup here, and this is the spectrum of the modulated wave corresponding to different data rates from 2 gigabit per second to 15 gigabit per second, and we can decode, demodulate this wave very good, showing that the upconversion was linear. In addition to that, we performed another experiment where we changed the LO frequency. So we can see that the device has a very broadband operation. So we can do this upconversion, and we can still have this modulated channel across a very wide range of frequencies from 70 gigahertz to 110 gigahertz. So it's basically more than 40 gigahertz of bandwidth. This is what we have, and this is very promising for telecommunications. So as a conclusion, we showed that in-device manipulation of electric fields can lead to extraordinary electronic properties. This was the concept that we showed in the Nature paper when I was at EPFL, and we obtained cutoff frequency of 18 terahertz. So we obtained excellent linear operation in on and off states, and this is very important feature for a switch. So we had IP1 dB above 6 watt per millimeter and IIP3 of 150 watt per millimeter. These are very high numbers. And when we bias the devices close to the threshold voltage in the nonlinear regime, we also obtained very high performance close to the theoretical limit of an ideal diode. And then integration of electronic meta-devices enabled high-performance switches that are very fast and have very good statics in terms of insertion loss and isolation. And we showcased the performance of these devices and their application in a 100 gigahertz QPSK transmitter operating at data rates up to 15 gigabit per second. So we believe that electronic meta-devices show promise for the next generation of telecommunication circuits, and I'm again grateful for this chance to present our work. Thank you very much.